Hello everyone. In this video we are going to do a hot air recirculation study over an LNG plant using CFD and OpenFOAM. So this simulation is yet another application of atmospheric boundary layer flow modeling. However, in contrast to the previous two simulations where we validated a atmospheric boundary layer flow as well as we used it in a pedestrian wind comfort case, we have a couple of new considerations to make in this simulations. Rather than working with a neutral atmospheric boundary layer, we will be working with a stratified atmospheric boundary layer, and also instead of working with model scale geometry, we will be actually working with a real scale geometry. And to cope with that, we have to follow concepts of roughness scaling rather than viscous scaling based on I plus. And I have organized the video like this. First of all, I will explain scope of the case study, what exactly are we trying to find out, and later we will talk about a couple of theoretical concepts that are relevant to the methods used in the simulation. For example, like what exactly do we mean by stratification, what exactly is thermal stratification, then also when do we use roughness scaling. Supporting to that, we will talk about a concept called MOST theory or Monin-Obukhov similarity theory, which helps us to model stratification in atmospheric boundary layers. After that, we will follow the usual CFD workflow, and we can explain things in detail as we do it. Okay, so let's start by discussing the problem. So we have a scenario where we are setting up a new LNG liquefaction plant, and we are in a stage where we want to optimize the plant layout in order to maximize the annual production rate. So if you consider a general LNG facility, you have reservoirs, pipe racks for transporting the gas, then you have heat exchanger stacks. So the one you see here with too many fans are basically heat exchanger stacks, and they will be working over at different temperature ranges. Some might be cryogenic, some might be pre-cooling stage, and so on. So they are some of the standard structures that you find, and you have some supporting buildings in between. So during an operation cycle, so if you consider an air-cooled heat exchanger, it will take in ambient air through the inlet, then it will extract heat from the natural gas, and then hot air basically exits through the exhaust. Heat exchanger being at the heart of the process, we want to study how the hot air exhausted from the heat exchanger is getting recirculated in the region, and we want to know whether that recirculation is affecting the inlet temperature of the heat exchanger itself, and thereby affecting efficiency of the process. Okay, so the goal of the simulation is to evaluate for a proposed plant layout subject to the environmental conditions or the atmospheric boundary layer flow. We want to evaluate how this hot air is getting dispersed into the surrounding. Okay, and we want to probe the inlet temperature accordingly. So that's the objective of the study. Okay, so depending on the presence of this reservoir tanks and the wakes created by the buildings, and also these pipe racks would kind of dampen the incoming flow, surrounding flow, so that acts as a barrier, and also the meteorological wind data has to be taken account, and depending on the direction of the wind, the wake structures may affect the hot air recirculation, and we want to basically study that so that we have better control over the operation of the heat exchanger. Okay, so that's the application or scope of the study. Investigate the amount of correction that we might need to account for at the inlet of the heat exchanger. Okay, so now we can look into some concepts that we will be using to set up the simulation. The first concept that we want to understand is stratification. So when we say that a fluid is stratified, we mean that the density varies with height. Okay, so you can have several different ways to achieve that. The one that we will be talking about in the simulation will be thermal stratification. That means we have a temperature gradient with respect to altitude. Okay, and if you consider ocean currents, perhaps you have salinity variation in the domain, and you can have density variation based on that. And also in compressible flows you have actually pressure driven density variation. Okay, so in our case we are talking about thermal stratification. So it can happen in three ways. So it can be either stable, neutral, or unstable condition. We have seen neutral conditions, so that's isothermal conditions. You don't have temperature gradients. But when we have stable stratification, you have temperature increasing with altitude, or you can say that density is increasing with depth, or you can also say that cooler fluid is near the ground and warmer air stays on top of it. Okay, so if you consider atmospheric boundary layer over the span of a day, during the daytime the soil temperature will be higher, and you have higher temperature air near the surface and lower temperature air on the top. So that's unstable situation. We can see how that works, but that's a case of unstable situation. But as soon as the night time happens and the soil, because of its thermal properties, loses heat faster and would render the nearby air cooler, and that's basically an inversion of the earlier case where you have higher temperature there, and that's a situation of stable stratification. Why do we say that it's stable? So if you consider a situation where you have temperature increasing with altitude, and consider a fluid parcel at some particular height, it has a density as a function of height. Okay, and then as soon as that fluid parcel tries to move upward, what happens? It is moving to a region of lower density. Okay, so the surrounding temperature is higher, and that would mean that the air there is less density. Okay, so as soon as this fluid parcel goes up, it would feel heavier than the surroundings, and it would dip down back to its initial position. And likewise, as it tries to move down, what happens? It's going to a higher density region because of low temperature, and that would feel lighter over there in the lower level, and because of that it rises back to its initial position. So because of the stable stratification, the motion is kind of suppressed there. Okay, so that's why it's called a stable system. Okay, the disturbances, decay, and the stratification versus motion. Vice versa, in the unstable stratification case, if you consider the fluid parcel, so there you have temperature decreasing with altitude, so that's similar to a hot pan. Okay, you have higher temperature near the pan, and as you rise up the temperature decreases. So over there, if a fluid parcel of some density tries to goes up, then the temperature there is lower, which means the density higher in the upper region. So since the fluid is moving from the lower region, it has a lower density than the upper level, so it means it will continue to rise up. Okay, and likewise, as it tries to sink down, because of higher temperature at the lower level, you have lower density air, and since you are coming from the top, you have a higher density, and it would continue to sink down. Okay, so the motion here is augmented by the stratification. Okay, so that's how stable and unstable thermal stratification works. So in our case, we are considering stable stratification because the stable stratification, as we saw, suppress this motion. and reduce the chance of buoyancy driven turbulent mixing. Okay, so in our case, so that's a kind of a worst case situation for the heat exchanger exhaust. The exhaust gases kind of stays around the heat exchanger stack without getting easily dispersed into the free stream. Okay, so that's why we are considering stable stratification in our simulation, okay, in order to study a possible worst case scenario. Okay, so the second concept that we want to talk about is wall scaling in turbulent boundary layers and how to model the near surface flow behavior. So we have seen the use of wall functions to model the near wall flow behavior, and in order to have a better fit between the wall functions and the actual velocity or turbulent property profiles, then we need to follow the proper scaling laws or similarity laws. Okay, in the case of ABL flow that we did using model scale geometries, the surface roughness is characterized by the aerodynamic roughness length, and since it's model scale, we had to scale down that characteristic length by the factor of 1 by 1000. That would mean that the roughness length is so small it falls within the viscous length scale and viscous layer. So the dominant mechanism is the viscosity. Okay, so and in that case, we place the first cell height in the log layer by estimating the wall y plus. So this wall y plus is basically derived based on similarity. Okay, similarly, so that was a situation when you have the surface roughness height to be very small and it has negligible effect. So in order to approximate the actual near wall flow behavior, we have to have the right y plus value, okay, for the wall functions to better fit that approximation. Okay, so that's a situation where you technically call it hydraulically smooth case, where the roughness has minimal effects. But in case of actual scale atmospheric or urban boundary layers, here the physical mechanism of momentum transfer is by the pressure drag by surface roughness elements like buildings, vegetation and terrain features. So that's an entirely different length scale, okay, and also a different mechanism. So here we can't rely on y plus values, but we need a appropriate length scale. So we have something for that in the literature that's called non-dimensional sand grain roughness height, Ks plus, and that is defined as this, where Ks is the sand grain roughness height, and that is related to the aerodynamic roughness length. Okay, and aerodynamic roughness length is the height where you when you extrapolate the velocity profile where it intercepts the y-axis. Okay, so that's that height. And you have friction velocity and kinematic viscosity. So by having this non-dimensional parameter, we can characterize the nature of the surface, whether it is hydraulically smooth or hydraulically rough. When you have a hydraulically smooth case, then you can follow viscous scaling and estimate the first cell height according to the y plus value. Okay, but in our case what we have is a fully rough situation with actual scale geometries. So then we have to rely on roughness scaling. Okay, and for that we use a dimensionless height of z over z0. Okay, and we have characterized the atmospheric boundary layer according to this ratio, and we want to place our first cell height accordingly in this range, where the z is between 30 times z0 and 0.1 times delta, delta being the height of the atmospheric boundary layer. During daytime you will have a certain height for the atmospheric boundary layer, and in the night time different value. Okay, so usually when you have stable conditions, then the height of the atmospheric boundary layer will be lower. Okay, and you have more turbulent mixing, then the height increases. So correspondingly you have to follow this thing. So the idea is that we have to look at the relevant mechanism and the relevant length scale. So you can still follow viscous scaling here, but that's unnecessary complication for us. Our mesh would be really big if we want to resolve the if we go for still resolving the y plus, which is of no use to us. So we in order for us to use the wall functions, we have to place the first cell height in this region. Okay, otherwise we will be under predicting or over predicting the near surface behavior of an actual atmospheric boundary layer. So that's the point. So during the setup we will be calculating the first cell height according to this requirement. Okay, so another theory that we want to look is the Monin-Obukhov similarity theory and the Obukhov length. So when we worked with neutral atmospheric boundary layer, we had wall functions and that approximated a perfectly logarithmic profile. But when you have stability to taken into consideration, the profiles deviate from logarithmic behavior, and to account for that, this theory is used. Okay, so the theory basically says that under these assumptions you can use a stability parameter derived from the factors of surface friction velocity, buoyancy, flux, and one common constant, a parameter that can be used to characterize all surface atmosphere exchange processes. Okay, so that's the basic idea, and a parameter which is the Obukhov length is derived based on similarity, and it basically quantifies the relative strength between shear driven mixing and buoyancy driven mixing. So in the numerator you have velocity square, which is representative of shear driven mixing, and in the denominator you have theta star, which is a function of the turbulent heat flux. Okay, turbulent heat flux is the thermal energy being convected by turbulence. Okay, and in the top you have kind of kinetic energy. So basically Obukhov length shows the relative strength of shear and buoyancy effect. Okay, so using this Obukhov length, we are using a stability parameter, a non-dimensional number, which is Z over L, so where Z being height from the surface. Okay, and by the nature of the Obukhov length, we can characterize between stable and unstable conditions, and also whether the shear dominates or buoyancy effects are whether comparable to the shear driven effects. Okay, when you have stable stratification, the ground surface is cooling, then the turbulent heat flux vector will have a negative sign and the heat is flowing to the ground. Okay, and theta star would be positive and the Obukhov length would be positive. Okay, so that's here Obukhov length should be positive, and when you have a unstable condition and surface temperature is higher, then the turbulent heat flux would be positive and the heat is going up, then theta star would be negative and L would be negative. Okay, so by checking the sign of the Obukhov length we can actually know whether it's stable or unstable, and also depending on the magnitude of L and the position from the ground, we can actually know the strength of buoyancy effects. Is it considerable in that region? Okay, so that's how this parameter is useful. And like I said, so the logarithmic profiles for the neutral condition gets modified, and in literature you can find the modified wall functions. So earlier it used to be u star over kappa ln z over z0. But now we have a new term, a second term, which is a function of z over L, the stability parameter that we saw. Okay, and psi m here are dimensionless functions. So you plug in to the function and you get a value, but they are not numbers. Yeah, you can look into that. But the key point is the wall functions are modified to account for the stability effects. So in OpenFOAM we will be using thermal wall functions, and also in that case we will be specifying the surface heat flux, and from that this additional term or the Obukhov length will be calculated, and then it will be used in the wall functions. Okay, so there are too many things, but the key point is that we have the wall functions modified to account for this. And you can read about this in detail in this article where it details about the modifications and also the universal functions that I mentioned to find the coefficients. Okay, here you have the length, and here you have the modified wall functions. So there are different classifications based on the magnitude of L, but in general, if it's negative it's unstable, and if it's positive it's stable. Okay, yeah, so that's how it works. So the final concept that we want to be aware of is with respect to the solver that we are going to use. So in general, the Navier-Stokes equation can be written in this form. So the final term, which is the body force term, will be modified to account for the buoyancy effects, and that's basically done using Bose-Einstein approximation. And according to that, you consider density to be a function of temperature, and if you calculate the body force term with this modified density, then you have a rho 0 g term, which is the weight of the fluid. Then you have an additional term which accounts for the variation in density due to temperature change, and that additional term is the buoyancy term, which is written below. So in the buoyant Bose-Einstein symbol form solver in OpenFOAM, we actually solve Navier-Stokes equation in this form. Also we will see that the pressure term will be a modified term. Instead of solving the total pressure, we'll be solving for the dynamic pressure. So the idea is that the hydrostatic part of the pressure actually balance the weight of the fluid, so we don't have to solve for that the solver. What we will be solving for will be the dynamic pressure part, and in the body force term what we will be having is this buoyancy force term. Okay, so define the solver, we will be specifying this beta coefficient of thermal expansion, and we will have this gravity file in the boundary conditions, and so on. So that's the final thing that we want to check. So we will be solving a modified Navier-Stokes equation with this Bose-Einstein approximation. Okay, so now we are all set. Now we can start with the CFD workflow. Okay, so let's take a look at the geometry first. So for the simulation, I'm using plan layout of a LNG regasification facility as a reference. So you can find all the basic elements in a LNG liquefaction plant here. You have the reservoirs, then you have the pipe racks, and most importantly heat exchanger stacks, and there are a couple of buildings associated with the process. Okay, and another thing is the location of the plant. So you have sea on the west side and on the south side, and in the simulation we will be considering a flow direction which is parallel to the length of the heat exchange stack. I had previously done a simulation where I investigate flow from the west side and how the weights of the tanks actually influence the recirculation from heat exchanger. But in this simulation we are considering flow along the direction of length of the heat exchanger stack. So I considered it because since the heat exchanger stack is very long, there is more chance that exhaust plume from the heat exchanger over the leading side can affect more over the heat exchangers present on the trailing side. So I have considered this direction, investigating whether it would be a worst case scenario. Okay, so I have reproduced this geometry in FreeCAD. So the reservoirs, the pink is the pipe rack, and you have the heat exchanger stack here and the supporting building. The pipe racks geometry will be actually used to mark the cells where you have the porous. If I hide pipe racks, and if you see the heat exchanger stack, I have actually modeled it as 3 different type of patches. You have the heat exchanger body, then you have the exhaust faces on top and the inlet faces on the bottom. Okay, so I have a total of 72 heat exchangers, and in the OpenFOAM I have grouped all the exhaust faces as a single patch, while in the case of inlet faces I have grouped each row along the direction of the length to be a single patch. So I have 18 rows and correspondingly 18 inlet patches. So I did it because I want to probe what happens with each row of inlet temperature. Okay, so having 18 different patches, I have better control of post processing. Okay, that's the only reason I did it. And also if I hide the inlet and exhaust face, and what remains of the heat exchanger is the heat exchanger body, you shouldn't have overlapping patches. If you have overlapping patches, that may affect snapping operation. Okay, keep in mind. The other thing is that when you have curved objects, it's better to have enough tessellation for it. So accordingly I have created mesh objects for reservoirs. So you can do that by basically going to the mesh module, and then if you select a geometry and create a mesh from shape, you can basically control the fineness of the tessellation by adjusting these 2 parameters. Okay, so I have already done that for the tanks and also for the heat exchanger body. Okay, yeah, if you just export it without having enough tessellation, then that can also affect the quality of your mesh. Okay, so that's enough. So that's our geometry, and I have exported these mesh objects and all other geometries as STL files and have stored it within the constant try surface folder. Okay, now we can move to set up the background mesh. So in order to set the domain, I have done some basic estimation of domain size following the best practice guidelines for atmospheric boundary layer flow. The storage tank height is 32 meters, so that's the tallest building in our geometry. And I have considered an imaginary building made using the smallest dimensions of the geometries that we have. And accordingly I have estimated the overall dimensions of the domain to be this, and also I have positioned the planned geometry to be at the center of the domain. That's why you see this terms in between. So 50 here is the minimum point of the geometry in x direction, and 450 is the maximum point. Also the inlet flow comes from the sea, and correspondingly I have considered the aerodynamic roughness length to be 0.003, which corresponds to a moderate to rough condition over the seesaw. Okay, so we are following roughness scaling, and accordingly the lower limit and upper limit of the first cell height is calculated as 0.09 meters and 20 meters. So our first cell height should be in between this, and I'm using 10 times the lower limit, so that's 0.9 meters to be the first cell height that I aim for. According to this, I have set up the block. So open the Linux terminal and navigate to your case folder. In my case, I have named it as LNG plant. Then go to the systems folder, then edit the background mesh file, block mesh tick. Okay, yes, the first part here is where you set the domain vertices. So according to the dimensions calculated, I have defined the coordinates. The second thing is to specify the cell count. So I have done a basic estimation of it based on the imaginary building dimensions, and okay, so that's the cell count that I'm going to use. And also I am not using gradings. Our heat exchanger is basically floating in the domain, I have found that with grading and when you have floating objects, it struggles to get the snapping proper. I always found that there are some cells which is of high skewness. So I have followed uniform grading, and I will have local refinement or volume refinement to get the first cell height requirement. And apart from this, in the block mesh file you have the standard patches, inlet, outlet, ground, and the lateral and top boundaries. So the domain vertices, the cell count, and the grading. So that's what you set in this file. Once you have done that, save it, Ctrl O and Ctrl X. Then you can go back to the case folder and create the background mesh, block mesh. Okay, so the meshing is done. We can do the snapping operation and then visualize the mesh in ParaView. To set the snapping settings, go to the systems folder, then open the snappy hex mesh dict file. Let's go one by one. I have disabled add layers. I'm not using inflation layers. So in the first, the geometry definition part, we include all the STL files. Just ignore the file name. Like I said, I had done a simulation with wind coming from the west direction, and then I rotate the geometry by 90 degrees to actually study the flow coming from the south. So that's why it has 90 in the file name. But the first file is the storage tanks STL file. Then you have the supporting building. Then you have the baffle geometry, which we will use it to mark porous cells on. Then you have the heat exchanger body, and then you have 18 inlet faces STL files. Then you have finally the exhaust STL file. Okay, and then you define the volume refinement regions that you want to have. So we will be using this to achieve the target first cell height. Then you define the refinement level for storage tank and buildings. I have used 4 and 5, and also I'm not using minimum and max, but instead uniform surface refinements. So this is where we specify that cells falling into the baffle STL surface is actually identified as a cell zone named baffle cell zone. Okay, we are actually picking the cells that fall into the STL volume and naming it as baffle cell zone, and we will use the cell zone in the finite volume options file to basically include the permeability source terms. Yes, then you have the heat exchanger body, which is given refinement level 4, and heat exchanger exhaust and inlet faces are given refinement level 5. Okay, so if you go to the end, you have the default inflation layer settings, but like I said, we are not using it. Then you have the mesh quality controls also included. So I have set the maximum skewness 4 and orthogonal quality to be 60. Okay, yes, so you have to include the STL files. Then you have to specify the cell zone for the baffle geometry, and then you specify surface refinement level and mesh quality. So that's what you do in this file. Then you save it, Ctrl O and Ctrl X. Once you have done that, you can actually run snappy hex mesh. Alright, it will take some time, so let's wait and continue from there. So the meshing is done. Now we can check the mesh. So run the command check mesh, and I have done that. The final mesh quality checks look fine, and you can find all patches. Just cross check that you have everything. Then in the final snapped mesh you have 2 mm. Now we can just view the mesh in ParaView. Open the form file, apply. If you don't have a form file, just create one in the folder, so you can easily view mesh and the results in ParaView. Let's check the mesh. So you have the volume refinement very near the ground, and you can basically probe the coordinates of the nodes by using this tool here. So if you check the first cell height, that's 1 meter, so the first cell center would be around 0.5 meters, and that's above 0.09 lower limit for log-low wall functions. So this is fine. And check the internal mesh. So we have the snapping, so you had reservoirs, the buildings, and you can just see the outline of that baffle zone, cell zone. Okay, This is how the internal mesh looks. Everything is sufficiently resolved. You can't actually see the baffle zone geometry because it's just a tool to select the cells for the cell zone. Here you can see the heat exchanger body, which is actually floating in the domain. Okay, and on the top you have the exhaust faces, and on the bottom you have inlet faces. So the mesh looks fine. Now we can actually start setting up the boundary conditions. So to edit the boundary condition files, go to the 0 folder. Let's edit the velocity boundary condition. At the inlet we have the wall function, which is called atmospheric boundary layer inlet velocity. So this is the wall function that we saw when we discussed the concept, and I'm considering a free stream flow with mean velocity 6 meter per second measured at 10 meters, and our direct flow is in the x-axis, lies parallel to the length of the heat exchange stack, and vertical is along the y-axis. So we have talked about this. Even though it says Z, vertical is along y-axis, and you specify the aerodynamic roughness length regarding the Obukhov length term that will be derived from the parameters in the temperature file. At the inlet we have the wall function, outlet you have zero gradient condition. Then at the heat exchanger patches, so the heat exchanger, basically we are considering it to be a black box, so we don't want to solve what happens inside the heat exchanger. From the operational data we know what is going in and what is coming out. We assume a steady state flow rate of 652 kilogram per second for 4 heat exchangers. Okay, so we know that net value, so we specify that, and it will be distributed among the patches. So you have 18 different patches, a total of around 17,500 kilogram per second of air is getting exhausted by the total heat exchanger stack. Okay, and the one more thing, so the heat exchanger inlet is actually an outlet with respect to the computational setup of the problem. Okay, so the flow is sucked into the inlet, and likewise the heat exchanger exhaust is actually an inlet to the domain. Okay, and we assume, like I said, steady state operation, the mass flow rate to be same going in and out. So correspondingly I have used the velocity for a diameter of the fan to be of 5 meters, and I have calculated it to be 6.8 meter per second. So that's how you set the boundary condition for velocity at inlet and exhaust of heat exchanger. Then you have the usual symmetry plane condition at top and sides. Okay, so the key thing is we are considering the heat exchanger block to be a black box. Right, so that's the velocity file. So save it, Ctrl O, Ctrl X, and the next we can take a look at the temperature file. So here again at the inlet we have the wall function. So this wall function basically sets the stable stratified temperature profile in the domain. That's called atmospheric turbulent heat flux temperature wall function, and the parameters are the Tref is basically ambient temperature, which is 25 degrees Celsius or 298 Kelvin, and then here Q is the surface heat flux. So since we are considering a stable situation, we have a heat flux which is negative, and then you have the aerodynamic roughness length and something called thermal roughness length. So that's around 1/10 of the aerodynamic roughness length. There is this effective alpha, which is alpha T. So we will see a separate file for alpha T. So, and alpha T is basically turbulent thermal diffusivity. So the main mechanism of heat convected is by turbulent mixing. So that's why alpha effective is alpha T rather than just alpha molecular thermal diffusivity. Okay, so we will see this file separately, and then you have the specific heat capacity and density of the fluid, which is air. Okay, so that's the inlet. So basically using these parameters you calculate the Obukhov length, and then you have the stability parameter set by L. Okay, so that completes the wall function. And at the outlet we are using an inlet outlet condition. So that's basically it accommodates backflow. So when you have multiple inlets and outlets, there can be backflow. at the boundaries, and it basically accommodates that. So right now the inlet value means that if there is backflow, then the backflow will be of ambient temperature. That's what this means. Okay, then at the ground and walls we have zero gradient condition. At the exhaust we set the temperature of the exhaust gas. This is also what we know. So it's 45 degrees Celsius and 318 Kelvin correspondingly. Okay, yeah, so this is the temperature file. So important thing, we have to set up the inlet wall function with the surface heat flux so that we get the stable temperature profile. So save it, Control O and Control X. Then we can look at turbulent kinetic energy. So again, I haven't changed much with respect to turbulent properties. So you have the atmospheric boundary layer wall function, the same inlet velocity, mean flow velocity, and outlet is again considered as the inlet outlet condition. Then you have smooth wall function over wall. At the exhaust, basically an inlet in our case. Computationally, we are specifying the turbulent kinetic energy based on assumed turbulent intensity of 5%. Okay, so that's how it's done for turbulent kinetic energy K. So save it, Control O, Control X. Now for epsilon, again you have the wall functions. At the ground you have atmospheric epsilon wall function. On the building surfaces you have smooth wall functions. Okay, and at the exhaust you have a fixed value computed based on relation between K and epsilon. Okay, and also here L is characteristic dimension, that's considered to be around 0.05 of the diameter, which is 5 meters. So that's epsilon, Control O and Control X. Okay, so we can also see the turbulent viscosity nano NUT. So this is where we specify the roughness to the ground. So you have the wall function and you specify the aerodynamic roughness length, which in our case is 0.003. Okay, so and go to the end. At the inlet we have used a calculated boundary condition, which means it will calculate the turbulent viscosity based on all other boundary conditions that we have prescribed. Okay, so save it, Control O, Control X. Now we can see the pressure file. So this is different from the normal pressure. We have something called PRGH. So this pressure is specific. The pressure file is specific to when we use Boyen-Bossin's simple form solver, and this is basically the dynamic pressure. So the total pressure minus the hydrostatic part. And again to note that we in OpenFOAM we are dealing with pressure over density. So density is already taken care of. Okay, and at the inlet we have this fixed flux pressure, so that basically allows the solver to adjust, or the pressure to adjust itself based on the developing flow. Okay, so we are not forcing the pressure to be some value, but we allow the flow to adjust itself. Okay, so that's used throughout. That's it for the pressure, but we need to have PRGH rather than having a file for P. Okay, so save it, Control O and Control X. So if I do an ls, then you can find other files. Yeah, so let's take a look at alpha T file. So this is also new when we use Boyen-Bossin's simple form solver. So alpha T. So this is like I said, it's a property of the flow field. With respect to every boundary we have to specify how turbulent mixing is causing convection of heat in the vicinity. Okay, so that's the purpose of this file. And near the ground where you have the stable conditions and negative surface heat flux, you basically use the wall function. And here there are a couple of parameters. So the Prandtl number is molecular viscosity over molecular thermal diffusivity, that's property of air. And you have the turbulent Prandtl number, which is a property of flow field. So if you have a higher value of PRT, it means that heat convection by turbulent mixing is actually lower. We expect it to be lower since we have a stable condition and turbulence is suppressed. Okay, so because of this consideration, I have used Prandtl number to be greater than 1, and if it's more towards the unstable side, then we will use some value less than 1. Okay, so and you have the aerodynamic roughness length. For the buildings, we have a smooth surface, so the aerodynamic roughness length is small, and also the Prandtl number is a bit less but still close to the stable behavior. Okay, so you can find or read about the possible values for turbulent Prandtl number from literature. So I'm using 1.1 and 1 for the simulation. Okay, and again, if you go to the end, we are using calculated for inlets and zero gradient for outlets. And one more thing, that throughout the boundary conditions file for the baffle geometry, we are either using calculated or zero gradient. You don't have to worry about what should be the boundary baffle. We will be specifying what exactly has to be done for the cell zone, baffle zone, cell zone in a separate file where we set a finite volume options. Okay, that's where we set that, so we can deal that later. So save this file, control X, and if I go back to the velocity file, then you can see that for baffle I have used zero gradient. Okay, yeah. What's left is href file, so that's specific enthalpy nano href. So we need this specific enthalpy file to set a baseline for the solver. We set reference enthalpy to 0 in the domain, and by that we are saying solver that consider the ambient temperature condition to be the reference enthalpy point or 0 enthalpy situation, and everything is reported with respect to that. Okay, so the exhaust gases are coming at a higher temperature, and that will have an enthalpy greater than 0, and all other surfaces are essentially at reference condition. Since the solver works with temperature changes, we need to bound the solution to a reference point. So that's the function of this file. Okay, so with the href, we have all the boundary condition files specified. Now we want to define the permeability options for our baffle zone, cell zone. For that, go back to the case folder and then to the systems folder, and here we want to edit the finite volume options file. So open that. Yes, so here I have added a block called baffle porosity. So this basically adds source terms to the Navier-Stokes equation and will be solved on the cell specifically marked in the cell zone. Okay, so it's a explicit porosity source type, and the model that we are using is a Darcy-Forchheimer model, and we have specified where to apply that in our baffle zone. So okay, so the Darcy-Forchheimer permeability model basically has two components. There is a viscous drag coefficient, which is based on the skin friction, and you have this form drag, which is basically a function of shape of the object. So that's the usual drag that we see in a bluff body, and when you have high Reynolds number flows, then form drag is more significant than skin friction drag. Okay, so we are more or less focusing on the physical obstruction to the flow rather than the skin friction drag. Okay, so and the other thing is you have three components, so that basically are the coefficients in each direction. So what 1 to 1 means is exactly in x and z direction you have some amount of resistance, and relative to that you basically have twice the resistance in y direction. So the most realistic way of modeling this term will be something similar like an anisotropic combination, and you basically want to quantify these values by perhaps measuring the drag force and dividing it by dynamic pressure. You can get the coefficients. Okay, and below it you have this coordinate system, so you can basically specify which coordinate system to follow in order to identify these XYZ directions. So in my case, I'm specifying that we can follow the global coordinate system, and the x-axis in the the global space is actually same as the length of the pipe racks. So in our case, if you remember the geometry of the pipe racks, it actually has a 90-degree turn. So to a certain extent, it is parallel to x-axis, then it is perpendicular to x-axis. So the best way to model that, or the most realistic way to model that, will be considering two permeable zones, okay, and one you follow the same coordinate axis, and in the next case you should rotate the coordinates by 90 degrees, okay. So then you have to modify it here, okay. So that's how you use this coordinate system block. But in my case, I'm just considering a single porosity cell zone, and to follow the same global coordinate system, okay. So specify which cell zone to apply to, and also the coefficients, and that defines the additional drag based source terms for our permeability model, okay. So we have that. So save it, Control O and Control X. Now we want to actually check the control dict file, and we have to set some post-processing functions and also a couple of solver settings to mention. So for that, type in nano control dict. You can modify the start from condition to be start time or latest time if you intend to pause the simulation. Like I said, it's always good to monitor the progression of the residuals and then adjust the under relaxation factors in between. So yeah, you can use that option for that. Then you have the standard CP and velocity probes as before, but particularly in this simulation I'm interested in having these probes for inlet temperature. So what I have is a surface averaged mass flow weighted inlet temperature, and I'm doing it for all the 18 inlet patches, okay. So you basically can keep note of this block if you want to reproduce, okay. And if I go to the end, I have a separate function. So in this simulation, I have tried to plot the residuals in real time as the solution progresses. So that basically helps you to keep track of the solution. And if you see that some equation is starting to oscillate, then you can control the under relaxation factor of that equation specifically in between. So I think visualizing the progression of residuals is important. So this block here basically prints the solver info, which is basically the residuals, into a dat file called solverinfo.dat within the post-processing folder, okay. And in a different script, I'm actually calling this dat file and plotting the entries from that, okay. So I have two new things in the functions block. One is basically to probe the inlet temperature, and the second one to keep track of the residuals, okay. So save it, Control O and Control X. So if I go back to the case folder, I have a file called plot residuals gp. This is where I have scripted to plot the residuals. So it basically calls from the solverinfo.dat file, and it calls the different columns and plots it with respect to the iteration, okay. So we can see that when we run the solution. So just save it, let's. Okay, so let's also look at the solver setting for that nano. Yeah, so here you have to specify the numerical solver for the pressure equation. So I'm using a GAMG solver. So this is PRGH, not just pressure, so please note that. Then you have the solver for temperature, and also you have to specify the under relaxation factors for pressure and temperature here, okay, additional to everything else. Okay, so that's it, solver and under relaxation factors. Okay, so Control O and Control X. And what's left in the systems folder is numerical schemes. So we have to introduce a scheme for temperature. So finite volume schemes. Here you need to include the scheme for temperature. Bounded goes up. Yeah, so that's it. Then save it, and now what we have to set is the gravity field. So that is required for us to calculate the buoyancy force term. So for that we have to go back to the constant folder. So cd constant, and if you do the ls here, then you can see the file called g, which is gravity nano g, and you basically specify a uniform field with value minus 9.81 in the vertical y-axis. Okay, so this one is needed. Then you have to set the thermal properties. So for that we need to have a file called thermophysical properties. So open that. So here you basically specify the properties for air and also thermal expansion coefficient that we will be using is specified here. Okay, if you remember the buoyancy term, that was 1 minus beta delta t g, so that beta is actually specified here. Okay, so Control O and the Control X. Then within the transport properties you have turbulent Prandtl number, then you have the beta T rough. So general properties that you need to have, and also the thermal conductivity, not one common constant. So that is again properties required by the solver. So have a file like this. Then you have finally you have the turbulent properties, where you specify the turbulence model that you want to use, and I'm using a RANS realizable K epsilon model. Okay, so it's the same as before. So I think now we have covered everything. So we walked through the boundary conditions files, then we set the permeability options, then we modified the solver settings, the numerical schemes, and also all the relevant thermophysical and transport properties that we want to have to solve. Okay, so everything is set. Now we can actually run the solver. So for that we have type in buoyant Kosinetsk symbol form. Did I get it right? Yes. Yeah, so the solver has started to run, and I'm opening a separate terminal, and if you navigate back to the case folder, and if I do an ls, you can see this plot residuals.gp file. So that's basically the script that I mentioned earlier. Yes, so the solver has started, and you have the placeholders for inlet temperatures, and we can enable the residuals window as soon as it starts to run the second iteration. Okay, so we have the first iteration completed. Now we can actually post residuals file. So you type in gnu plot plot residuals gp, and that basically opens the residuals window. Okay, so here you can actually see the residuals progressing in real time. Okay, so it's running fine. So now we can wait for convergence and check the results. So the solution is almost converged. The residuals are low, and if you check the temperatures at the inlets, you can find that for heat exchangers between third row and sixth row you have almost more than 1 degree rise in temperature, and then you have a couple of heat exchanger rows where you have less than 1 degree rise in temperature, and towards the trailing side you have more than 1 degree rise in temperature. So this is what we wanted to check, how much does the inlet temperatures change with respect to the ambient temperature. Okay, so let's wait for final convergence. So the residuals are right now in the order of 10 to the power minus 5, and everything is looking fine, and with the plot you can actually see it's really good. So in one of the runs that I did, at some point the temperature showed some oscillations, then I reduced the under relaxation factor, and then it became converging again. Okay, so it helps to have this plot. Yeah, so if we have convergence, solution is fully converged in 564 sections, and these are the final temperatures. Okay, so that's the preliminary result that we have. Now we can open ParaView and see how the recirculating airstream is actually influencing the inlets. Okay, so I have loaded the result files in ParaView to once again take a look at the temperatures. We saw that almost all of the heat exchangers except the first one had significant temperature rise, and many had at least 1 degree of temperature rise at the inlet. Okay, so now let's try to understand how is that happening. First of all, I had created a velocity slice just to show you the wake structure, and clearly you can see the permeable zone which is causing significant damping to the flow. So this is how the velocity plots look. I have created a slice to see the thermal plume from the heat exchanger, so it's significant amount of area is affected by it, and also most importantly the lower part, the heat exchanger, is also affected. So here you can clearly see that, so the minimum here is 298, and apart from the first two heat exchangers over the leading edge, almost all the others inlet region is affected by the exhaust temperature. Okay, so we need to somehow block the exhaust gases reaching the inlet area. Okay, and I have also created a vector scene, so basically you can see that some recirculation, especially over the side, is present. So here over the sides there is this, the temperature of the incoming flow is risen prior to going to the inlet. Okay, so this is also affecting the inlet temperature, and to better visualize it, I have also created stream tracers. So you basically position them at the inlet patch, and then you can basically integrate backwards, so you can know that how the incoming flow is affected by it. And I have given coloring based on temperature, so that's how I have created this. And so you can see that the incoming flow is passing just above the heat exchanger, and there the temperature is getting increased. So the incoming airflow is getting heated up here, and it's going to the inlet. Okay, so that's not very good to have. Yeah, and you have this building here which is also affecting the incoming flow. So when you have a wind direction which is inclined at some point and over the storage tanks, then that can be interesting to investigate. Okay, yeah, it looks very cool. Yeah, so it's basically the air which is coming from the top region is getting heated up because of the plume from the heat exchanger. Okay, yeah, so you can basically see that a significant region is heated up because of the exhaust gas, and here you can see that the inlet stream is also getting heated up by the exhaust plume. Okay, yeah, yeah, okay. So I think this was a good case study to do, and you need to basically evaluate multiple directions before we arrive at conclusions. But I think I have demonstrated a single case, so you can try it out. Okay, so thanks for watching.